So managers often base their decisions on analysis of uncertainties, such as the following. What are the chances that sales will decrease if we increase our price? What's the likelihood a new assembly method will increase productivity? What are the odds that a new investment will be profitable? So probability is a numerical value that describes the chance that something will happen. The closer the probability is to zero, the more improbable that event is. The closer the probability is to 1, the more likely it will happen. Three terms used in the study of probability are experiment, outcome, and event. An experiment is the observation of some activity or the act of taking some measurement, like tossing a coin or asking a question. So here the experiment would be rolling a die. And then all of our possible outcomes would be 1, 2, 3, 4, 5, and 6. And then our possible events that could occur would be observing an odd number, observing an even number, and observing a number greater than 4. Okay, so there's all kinds of things that we might be looking at. In statistics, the notion of an experiment differs somewhat from that of an experiment in the physical sciences. In statistical experiments, probability determines our outcomes. Even though the experiment is repeated in exactly the same way, an entirely different outcome may occur. So for this reason, statistical experiments are often called random experiments. So our sample space is the space of all possible outcomes, that set of our possible outcomes. So if we have our example of Bradley Investments, we have two different stocks that they're invested in, Markley Oil and Collins Mining. So Markley Oil has the possible outcomes of gaining 10, gaining 5, no change, or losing 20. And then Collins has the two outcomes of gaining 8 or losing -2. So all of those possible outcomes make up our sample space. So let's look at counting rules. So in general, you're going to be looking at part out of all the possible outcomes. But, how do you determine what are the appropriate number of possible outcomes? One of the things that you can use this for would be counting rules. So you have multi-step experiments where you have different phases. So an example of a multi-phase experiment is our Markley Oil and Collins Mining example. You might be looking at some subjective probabilities. You might be looking at how many random groups of 3 you can have. You might be looking at situations where the order matters. Sometimes it doesn't. So all these different rules kind of come into play when you're looking at this. There are 3 formulas that are useful in determining the number of outcomes in an experiment. This is the multiplication formula that is used to find the total number of arrangements for 2 or more groups. Sometimes it's helpful to look at this in a tree diagram. So let's look at an example and then we'll go through a tree diagram as well. So going back to our Bradley Investments example, we have Markley Oil that has 4 possible outcomes, Collins Mining that has 2 possible outcomes. So when we multiply these two together, we see that we have a possibility of having 8 outcomes. And so if we graph that out in a tree diagram, we see that Markley Oil has our 4 possible outcomes. Each of those 4 possible outcomes can then experience one of 2 outcomes with Collins Mining, allowing for us to have an entire set of experimental outcomes being these 8 observations that we see here. You'll use the permutation formula when the order of the objects is important and to find the number of R objects selected from a group of N objects. So remember, by definition, 0 factorial is going to equal 1. And Excel has a formula that helps with calculating permutations. So our number of permutations in a group out of our set of objects taken a small sample at a time is what we're doing here. Okay, so here we have this example where we have our media company is producing 1-minute videos, advertisement segments, and we have 8 different video segments that were made, and we want to figure out what combination of video segments we have to make up that 1 minute. And so we're going to use our permutation formula where we end up with 336 possible combinations, because here that order is going to matter. Here, with combinations, the order doesn't necessarily matter. The combination formula is used when the order of the objects is not important, and it's used to count the number of R object combinations from a set of N objects. So logically, the number of combinations is always going to be less than the number of permutations, because in permutations, the arrangement of 1, 2, 3 versus 3, 2, 1 are two distinct groups. But with combinations, 1, 2, 3, and 3, 2, 1 are treated the same, because we have the same observations within those groups. So when we have Grand 16 movie theater trying to figure out how they're going to do teams of 3, they have a possible of 35 different groups of 3 employees working at any given time. So how do we assign probability, right? So there are two basic rules that we need to look at when we are assigning probabilities. One is that it is assigned a value between 0 and 1 inclusive. So that means your probability can be 0, your probability can be 1. But when we take all of our outcomes and we add them up together, our sum of our probability values needs to equal 1, or 100%. We have three main approaches to assigning probabilities. We have the classical method, which is assuming that all outcomes are equally likely. We have the frequentist interpretation, or the empirical probability, and this is where you're going to look at experimentation or historical data to assign that weight. And then you have the Bayesian or subjective method, that's going to be assigning probabilities based on a judgment. So with classical probability, it's often applied to games of chance like playing cards and rolling dice. It can also be applied to lotteries, since the total number of outcomes is known before the experiment. If the set of events are collectively exhaustive and mutually exclusive, the sum of their probabilities will equal 1. And so mutually exclusive means that you can't have one occur while the other one occurs. And collectively exhaustive means that we're looking at all the possible events. So when I'm looking at my classical probability example, I have an automobile dealer wants to advertise for just under $30K that you can buy a convertible, a two-door, or a four-door model with your choice of either wire wheel covers or solid wheel covers. So if we look at this, we see, okay, we have type of car with 3 levels, and we have 2 types of trim on my wheels. So this is a multi-phase project. So if we think about it, how many different vehicles can the dealer offer? Well, if this is a multi-phase experiment, then we need to set up that we have a M times N situation. So we have a convertible with wheel covers, one without. We have a two-door with wheel covers and without. And then we have our sedan or four-door with wheel covers and without. So we can see this demonstrated in our pictures, but we can also find it through our multiplication formula of 3 times 2. So what would be the probability that a convertible with wire wheel covers is selected? And we're assuming that it's a random selection at this point. So that would mean that random selection would be selecting 1 out of the 6 that we have available. With the frequentist interpretation, it's often called the empirical probability. It's also known as relative frequency approach. So an example of a firm using empirical probability is, for example, life insurance, when they use past data to determine the acceptability of an applicant, as well as the premium to be charged. In another example, we have NASA has 121 successful flights out of a total of 123 flights. Therefore, the probability of a successful flight in the future would be 98%. So with the frequentist interpretation, the probability of an outcome is the proportion of times the outcome would occur if we observe the random process an infinite number of times. A common misunderstanding of this is that the random processes are supposed to compensate for whatever happened in the past. And this is just not true. It's also called the gambler's fallacy or law of averages. So you really got to keep in mind with law of large numbers that it's random. Okay. Here we have another example of the empirical probability where we have Lucas Tool Rental would like to assign our probabilities to the number of car polishers it rents a day. Office records show the following frequencies for daily rentals for the last 40 days. So what we do here is we have our number of polishers rented and the length of time that for which they're rented. So each probability assignment is going to be given by dividing the number of days by the total frequency or by the total number of days. So we're able to get that out of our days here, out of this time, our number of 0 polishers rented is going to be 4 out of 40% or 10%. 4 out of 40 times days or 10%. If there's little or no data available, probability can be estimated subjectively. A subjective probability is based on whatever information is available. An individual will evaluate the available information and then assign a probability. So when economics conditions or a company's circumstances change rapidly, it might be inappropriate to assign probabilities based solely on historical data. A great example of this would be trying to forecast sales in the last 2, 3 years, right? If you're looking at what was happening in 2018, 2019, and then try to use that model in 2020, the chances are that probability was not quite accurate for your projections. So we can use any data available as well as our experience and intuition, but ultimately a probability value should express our degree of belief that the experimental outcome will occur. So our best probability estimates are often obtained by combining the estimates from our classical or relative frequency approaches and our subjective estimates. So here we have a set of probabilities that one of the analysts has made for the different experimental outcomes. But notice when we use the subjective method, we don't necessarily justify why we think our different probabilities are the way we have assigned. So some things to keep in mind with events and their probabilities. An event is the collection of sample points, and the probability of any event is going to be equal to the sum of the probabilities of the sample points in the event. And if we can identify all the sample points of an experiment and assign a probability to each of them, then we can compute the probability of that event occurring. So looking at an example with our Markley oil being profitable, we can use Bayesian approach to determine the probabilities of the outcome. So the experimental outcomes, or the set, when Markley oil is profitable are those where the first value in the experimental outcome is positive, and these cases are going to be indicated in red. So therefore, we can calculate the probability that one of these events occurring by adding their probabilities together. So if we go and we look at our chart, we have the probability of 10, 8 happening is 0.2. Probability of 10, -2 is 0.08. Probability of 5, 8 occurring was estimated to be 0.16. And our analyst gave the probability of 5, -2 a probability of 0.26. So we can calculate the probability that one of these events occurs by adding them together. So the probability that we have an event where Markley oil is profitable is 0.7. The experimental outcomes when Collins Mining is profitable are those where the second value is, I'm sorry, the first value is profitable. And these cases are now indicated in red. So we can follow the same process to calculate what our probabilities are, and we find that the probability of Collins Mining being profitable is 0.48. So when we look at our different approaches overall, we have objective versus subjective approaches to probability. Our subjective is going to be based on whatever information we have available and whatever we use to make our judgments. Our objective approaches include classical probability, which is based on equally likely outcomes, or empirical probability, which is based on our relative frequencies.